Hello and welcome to another video. In this video we're going to be working on walking robot simulation. And in this one you're on an XY plane, it's an infinite plane, and you start at 0, 0 facing north. And the robot can receive a sequence of 3 possible commands. So you can either turn left, turn right, or move K units forward one at a time. And some of the grid squares are obstacles, so if we're at an obstacle and we run into it, we basically just stay where we are, we can't walk into it, and then we just do the next command. Return the maximum Euclidean distance the robot ever gets from their original origin squared. And so the Euclidean distance squared is just the x value squared plus the y value squared. So we can put that over here. And they tell you north is up in the y, east is up in the x, and so on. And there can't be any obstacle at 0, 0. So I found this little graph. So we start at 0, 0, so let's take a look at these. So we have no obstacles here. So our first command, we start off going north. So we go north, then east, then south, then west. And if you think about it, if you're looking forward, turning right, you would go from north to east. Then if you're east, you turn right and turn right this way. So turning right means we go to the next one this way, and turning left means we go to the next one this way. So from north, we'd go west, and so on. Okay, so we start off going north, and we go to 4. So we're over here. And this Euclidean distance is y is 4, x is 0, so this is 16. So this is our best, so we'll record 16. Then we turn right. So remember, turning right just means going east. And then we want to go 3. So 1, 2, 3. So we're over here. So if we're at 3, 4, the Euclidean distance is 3 squared plus 4 squared, which is 25. And so that's the best thing. So that's what we return. So that's the first one, 25. Okay, now let's look at the second one. So in the second one, there is an obstacle at 2, 4. So right over here, and we can maybe put like an X. Okay. And so now here, so we can go up 4. And then we want to turn right. So we go east. Then we want to go right 4, but we can't go right 4. We can only go right 1, and then we're kind of stuck. So this is our best Euclidean distance so far. It's the farthest away. So this is 4 squared plus 1 squared, which is 17. And then we want to turn left. So left means north again. And then we want to go up 4. So we would go up 4. So we'd go up to a value of 8 here. So this value would be 1, 8. And then this is 65, I think. Yeah, so that's our answer here, 65. So hopefully that makes sense. And then the last one, let's see. So we go up 6. So up 6, so up here. And this will be, oh wait, let's check if we have any obstacles. We don't. So we go up 6, and then this is, the Euclidean value here is 36, right? It's just 0, 6. And then we turn right. So turn right just means go to the next one. And then we turn right again, go to the next one. And then we go down 6, so we just go back down to 0. So this is 0. So our best is 36. Okay. So basically, the first thing you want to do when doing this kind of problem is figure out, okay, given this, can I do a simulation, or are the constraints too big to do a simulation? Do I have to do some kind of optimization? So here, if you look at the constraints, there's 10 to the 4th commands, and every command is up to 9 moves. So let's say all your commands are moving. You'd basically have 10 to the 4th times 9, which is fine, which will just pass. So you can actually just do a simulation of this, and that will be fine. Because, yeah, like basically, and also your obstacles length is kind of small. That's another thing. If you had like a ton of obstacles, maybe you couldn't do it, but you can. So what we can do here is we can just say first, let's store our obstacles in some way. Right? Store obstacles in SAT or map or something that we can access them in O of 1. So when we move to a square, like if we're over here, and we can move 1 square at a time because we acknowledge that we can just move 1 square at a time. Like if we have to move some squares, we can move 1 square at a time, and that will give us enough time to finish this. So we're going to be at some point, we're going to have some direction we're going, and we're going to move some number of squares, and we're basically just going to keep trying to move until we hit an obstacle. We can never go out of bounds. And then once we're there, we can calculate the Euclidean distance. So it'll be like store obstacles in a set, keep your position, and then just go through commands. If it's a turn, then turn. Otherwise, move one square at a time and record distance every time and just maximize that. So that's kind of the idea here. We're basically going to keep our position. If it's a turn, we're going to turn, and otherwise move one square at a time. And like I said, if it's a turn, then turn, it's pretty easy. So we can just get an array for these things. So north, if you think about it, if you have x, y, north would be this, right? We move up on the y. East would be this. South would be this. And west would be this. And so we can just have an array of these things, and then we can just say, like, okay, we start off over here, and then if we go left, we will go left, and if we turn left, we will go left in this array, looping around, and if we go right, we'll go right in the array, looping around. And then every time we move, we just take our current position and add whatever thing we're at to go to the next one. And if we ever hit an obstacle, then we just stop. So like if we're over here and there's an obstacle over here, then we will basically go here, and then now that there's an obstacle, we can't move anymore, so we just stop and we go to the next command. And then for every square we manage to get to, we just calculate the Euclidean distance and we return the best. So simple simulation, I don't think you can optimize it for like some shortcut thing, but sometimes you can optimize for a shortcut, so you do have to kind of like play around with the simulation, figure out is there some pattern you can optimize. Yeah. But the first thing you should do is figure out, can a simulation work? And code up a simulation, and then you can see if you can optimize. So a simulation does work. If your simulation didn't work, then you would have to optimize. Okay, so that's what we're going to code. We're going to code a simulation of this. So we're going to have these obstacles. Obstacle, and we can call this like obstacle set. And so these obstacles are basically like arrays. And in Python, you can have a tuple or something like that, but here you can't have a tuple, right? So we need to figure out a way to hash the obstacle. And one trick to hash an obstacle is, if you look, obstacle is at most 3 times 10 to the 4th. So we can just take the x value plus y times 3 times 10 to the 4th. We can make it like 4 times 10 to the 4th or something a little bit bigger than this. And that will give us a unique key every time. So you can just take the biggest value x can be and just add something bigger, and then that'll work. Okay, so this is what we're going to do to get a unique hash value. So let's do that. So we can just say, like, for every obstacle in obstacles, you can also do a string if you want, so you can get like the value for one with like a comma or some separator. But this is like the other really common way. So obstacle set add, or obviously Python just use a tuple, way easier. So. And then, yeah, this shouldn't be big enough to overflow. So this will be fine. Obstacle 1. And then, yeah, we can just add anything bigger than 3 times 10 to the 4th. So we can add like 4 times 10 to the 4th. So 40,000. Okay. And then we're going to get our directions just like this thing. So we're basically going to copy this thing here, and that'll be our directions. So array directions. 0, 1, 1, 0, 0, negative 1, and negative 1, 0. Okay, and then our like result will be 0, and we'll have our initial x and y, so x0, y0. And our direction that we're going in, so maybe we can call this like durs, and maybe we can call this like dir or something, will be 0, because we started off going north. And now we can just go through with the commands and do a simulation. So we can say for int command and commands. So I guess we have the -2 and 1. So let's just double check. So -2 means left. So if command equals -1, or yeah, I guess right is, yeah, so this one's easier. So if it's right, we will just add 1. So we can just say direction equals, and then if you want to loop around with an index, all you do is you just add 1 and you mod it by the length of the array. So if this is like 0, 1, 2, 3, when you get to 4, you'll do 4 mod 4 and it'll go back to 0. So we can do that. And we can just say this is dir plus 1 mod 4. And if we have the other one, then we have to do a minus. Minus 2. So here it's slightly trickier because I think in Java, like modular arithmetic is weird. So because, like, let's say we're here, if we do a -1, then we'll be at -1. So we don't want to get to negatives. So we have to figure out a way how to not get to negatives. So there's another trick you can use, or you can use mod. And basically what you can do instead is you can do something similar. So here we're adding 1 to go right. But if you think about it, so if we're here, we need to go left 1, which is here. And if we're here, we need to go left 1, which is 1, 2, 3. So it's here, and so on. So instead of adding 1, we can actually just add 3. So if we're here, then we'll go here, which is where we want to be. It's the same thing as going left. If we're here, we'll go 1, 2, 3, which is the same as going left, and so on. If we're here, we'll go 1, 2, 3. So hopefully that makes sense. So this is the same as going left, and this is basically the length of the array minus 1. So same kind of thing. And now the last one is just the actual going places, right? So we can say dx equals direction 0, and dy equals direction 1. And so we have to check if we go there, then can we actually go there? So we can just have a loop there. So we can call like int step equals 0, step is less than command. So we'll just go one step at a time. And okay, and so we can get our new direction. So int new x equals x plus dx. And new y equals y plus dy. And then we basically have to check, is this in the obstacles? So if obstacle set contains new x plus, so the same thing that we did here, so new y times 40,000, then we're fine to change these values. So x equals new x and y equals new y. And then we can calculate the max distance. So our result equals the maximum of the old result and x times x and y times y. Otherwise, if we hit an obstacle, we can just break immediately. So. And finally, return result. And let me just make sure I did this part right. So this will be the step that we're taking. And then new x is x plus dx. Yeah, so basically we're not using this step at all, so that's fine. And yeah, so we're just going to be looping like steps times. Essentially, this can be whatever value you want. You can be like unused if you want or something. Yeah, this is fine too. I don't think you can do underscore in Java. In other languages, you just an underscore. But basically, we just keep adding. We just keep adding wherever we're going. We check, is it an obstacle? If it's not an obstacle, we update our position and we get the distance. Otherwise, we break. That should be it, I think. Okay. Obstacles. Obstacle. Misspelled it or something? Oh, this should be 1. Okay. No suitable method. Oh, this should be plus. All right, there we go. Okay. And yeah, so generally I talked about this before, like if you have a set of integers, it's gonna be faster. You could have done this another way with like an obstacle 0 plus like a column plus obstacle 1 or something. But generally, integers are going to be the fastest thing. You could probably make an array as well here, which would probably be even faster, like an array up to some length with booleans would probably be even faster than set, but whatever. Don't care that much. Okay, so let's figure out the time complexity. So we're going through every obstacle, so that's we can call that like of obstacles, which is we'll call that M. or like obstacles or something, I guess. So we're going through every obstacle, putting it in a set. Then we're going through every command, and then for every command, we're basically brute forcing the command, but the command only has the command can only be up to 10. So I'd say this is basically constant time, because this can only be up to 10. So I'd say it's like obstacles plus commands. Getting a square of a value is also not constant time technically. I think it's like logarithmic. But I mean, the numbers are so small, it doesn't matter, right? You do like log of like whatever this biggest thing can be, like 40,000 or something. That basically ends up being like nothing as well. So I'll just say it's constant time. And then in the space, so we have this obstacle set, which is obstacles. And we have the directions, which is constant. And we have our current direction, which is nothing also. Yeah, so I think it's just the obstacle set. Yeah. Okay. So yeah, that's going to be all for this one, I think. Hopefully it's helpful. Definitely, like I said, the first step is figuring out, can you simulation? Is a simulation going to fit? If you can simulation, is there something better? And that's the approach I would take to these kind of problems. And also, when you do have these like things you can do, you definitely always want to start with the simulation, just like play around with like, okay, if I put stuff here, how does it work? And am I seeing patterns? And if I can see patterns, maybe I can simplify some stuff. But I always start with like playing around with like the thing they give you. You can call this like a game problem, where they give you like some game you can play, and then they ask you for something with that game. And then a lot of times in that game, there's a lot of simplifications that you can make and stuff like that. And the easiest way to do it is just like actually make the game like kind of like I did, with like a graph, and move stuff around and see what happens. But yeah, it's going to be all for this one. Hopefully you liked it. If you did, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.